Okay, so this is the second problem of the 4 that we did in class on March 16th, which was our last day together as a big group. So this is a topic that is called separable differential equations. So separable differential equations. And I'm going to use the same differential equation that we used with the slope field that we drew in the previous video, and that is dy over dx equals x over y squared. And what we're going to do with this very specific kind of differential equation is we're going to find a y equals, so a solution for it. And if you remember from drawing the slope field, I gave you an initial condition which allowed us to sketch in what looked to be a graph that followed a particular path. This is actually going to allow us to define that graph as a function. And it only works with a specific kind of differential equation. And again, differential equations are an entire semester course in college. We're just looking at a very, very small subset of the overall topic. So separables, what a separable is, it means you can literally separate it or pull it apart. And if you think about dy over dx, that's our y prime, that's a slope. It has a numerator and a denominator that are separate from each other. Now we tend to keep them together when we talk about the derivative as a noun, but if we think of the rise and the run as things that could be pulled apart or manipulated separately, you get this concept of a separable differential. So what we're going to do is a really old mathematical skill of cross multiplication. So on this particular problem, I'm going to cross multiply. So dy times y squared, or I'm going to write that as y squared dy, and then x times dx. And that creates an equation that still has the dy dx, still has the y squared and the x. You're just writing it horizontally versus as two fractions equal to each other. And then what we're attempting to do is to get y all by itself. So it's going to involve a few steps, obviously. But the first step is a calculus step. What we want to do is we're going to integrate both sides. And by integrating both sides, that in essence gets rid of the dy and the dx. So by integrating both sides, we're going to create an expression that looks like y cubed over 3. And I'm going to leave a little space, and then x squared over 2. And since these are indefinite integrals, technically speaking, we need a plus c on both sides, but they're going to be two different constants. So like a plus c and a plus d. And if I were to do that, and actually I'm not going to, well, I'll write that over here. So if I were to actually truly write in a plus c and a plus d, which I don't want you to, then to isolate y, you're going to have to subtract that constant from both sides. That'll be your first step if you were doing it that way. And then you'd arguably use maybe letter E or something like that over here for whatever d minus c is. And I don't know what d minus c is, but I do know that you're going to get it looking in this format where you've got y is isolated and the letter all by itself. So the convention is knowing that we want to get y all by itself. Just leave y cubed over 3 by itself and put a single plus c. And what that's doing is it's incorporating this notion that you're actually getting a constant on both sides that are going to be combined into a single constant term or constant expression on the side that the x is. In this case, that's our right-hand side. And then from here, to isolate y, it's a common set of steps. I'm going to go y cubed, and that's going to be 3x squared over 2. So I'm going to multiply 3. I'm going to multiply both sides by 3. So 3 goes to both pieces, and then I'll call that a 3c. And then from there, that's an equation that has y all by itself. I'm obviously going to take a cube root, but in order to solve for c, I also need to be given an initial condition. And I think in the video I made for the first one, we did y of 0 is 2. So let's use that initial condition, that same one that we used on the slope field. So if I take the 2 and I plug it in for y, so this is going to be using the initial condition to solve for c. And that's how these things come. They come packaged as one part. Oops, that was fun. One part, which is, look at all that jumping around, the differential equation itself, and then a second part that is the initial condition. So by using the initial condition, I'm going to get a specific y equals curve. And so in this case, that 2 is going to go in. I'm going to get 2 cubed. 0 goes in for x, and that zeroes this whole thing out. And then I've got 3c is this expression. So then 2 cubed is 8. So I've got 8 equals 3c, so that means c is 8/3. So c would be 8/3. And what that means is, okay, now we can take and write y cubed equals 3x² plus 3 times 8/3. Because I'm just going to take and plug in for c. And of course, 3 and the 3 there cancel, and we'd have y cubed equals 3x² 2 + 8. And then I'm going to cube root both sides. And when I cube root both sides, I can either write that as a 1/3 power, or I can write it as a literal cube root. That gives me a y equals expression. That y equals expression is then the curve that we graphed on our slope field. So this is how you functionally describe that curve. And that's really all there is to it. For it to work, you need an initial condition, otherwise you wouldn't have been able to solve for c. And then you need a separable differential equation, an equation that when you do this cross multiplication, you get all the y's grouped with the dy, and you get all the x's grouped with the dx. And there are a few more kind of challenging examples with this, but this was the example that we looked at in class. And I think maybe I used a different initial condition in class. I believe I might have used y of 0 is 3, but it functions the same way. It just is a different starting point on the slope field. So hopefully this helps, and this is installment 2 of the 4 pieces that we did in class on Monday, March 16th.